Hey, this is Leach with Simpson Math. In this video, we're going to be talking about some basic probability rules. We'll be looking at a few examples. So let's get started talking about probability rules. Well, a little bit of a pun because it's not just the rules of probability, but it's probability rules. Math jokes. Okay, so just to recap a little bit of review, these two things we should already know: that a probability is a number between 0 and 1 inclusive. And that the sum of all possible outcomes must be 1. We refer to that all the possible outcomes as our sample space. So the probability of getting a value out of our sample space is 1. Or sorry, probability of getting anything out of that sample space. So the probability of your sample space is 1. All right, let's talk about a few more specific new things. Let's talk about the term complement. So the complement of the probability of A is the probability that A does not occur. So just talk about that idea. So this is a thing that you should be pretty familiar with. Suppose someone says, oh, there's a 40% chance of rain on Monday. Oh, innately you go, oh, well, there's a 60% chance of rain. Sorry, 60% chance that it does not rain. Let me say that again. If there is a 40% chance of rain on Monday, then that means that there's a 60% chance, 1 minus the 40%, or 100 minus the 40% chance that it does not rain. So that should be pretty intuitive to you. So the complement of A is a probability that something does not occur. So I would write it as this: the probability of A, and then we put a little superscript C, kind of like it's an exponent, and that is equal to 1 minus the probability of A. We call it the complement, not that it's like complimenting like ooh girl, those shoes are nice. Not that kind of compliment, but complement as in it completes. Think back to your geometry class, you might have learned about complementary angles, two angles that add together to give you 90 degrees. Well, this is the same thing. These are two probabilities that add together to give me one whole 100%. So they complete each other. That's why they're the complement. They add together to give me one whole. So with this algebra here, if I have this thing, the probability of A complement that equals 1 minus the probability of A, I can solve for each of those. So notice if I add together these two things, it equals 1. We get that because if I add the P of A to both sides, I would end up with this first line. So if I add my two things, they equal 1, which is what I just said. They complete each other. And then similarly, if I was to take this right here and then subtract the P of A complement minus P of A complement. Well, wrote that weird, but it's this right here. I would get 1 minus the P of A complement. So notice, if I want to know what a certain probability is, and I only know what the probability of it not happening is, you just do 1 minus. So in some ways, those are kind of interchangeable because they are. It's all just based on your POV, just based on your perspective, your point of view. So let's talk about some notations that you'll see. I'm using today this A raised to the C for not a complement. You also will see it this time with a little prime, little tick mark, or you can use a tilde in front to kind of summarize to me not. I often will just half the time when I'm doing this, I'll just write not A. So all these things mean the same thing. Today I'm using this exclusively. This is maybe my next favorite one that I just use. I just write what it means in words. And so that's that. All right, so let's take a look at this example. This example it's gonna show up for parts C and D a little bit later. But let's take a look at this first one. At your school, 16% of the class are marketing majors. You're all randomly assigned to 2 partners in your statistics class. This question's a little bit weird. I didn't write it, but grabbing it from one of my courses. But just wanted to address it in case one of my students sees it. It's a bit odd because maybe basically I'm just imagining it's a really, really, really big class. Not our little, typical college class, but it's a really big class. And so that way we're not worrying about weird independence issues. So independence issues, which we might talk about later. At the end of the day, don't overthink probability questions. If they're not telling me how many people are in this class, or how many marketing majors there are, how many total people, then that's not a thing that they're wanting you to calculate. We're going to be treating these as independent events. So what's the probability that my first partner will be a marketing major? Well, there's a 16% chance that I get a marketing major, so that would be a 16% chance, or 0.16. My directions just say to write it as a decimal. What's the probability that it won't be a marketing major? Well, this is the complement. So if there's a 16% chance that they are marketing, then it's 100 minus 16%, or 1 minus the 0.16, and we get the 0.84. I often want to do math like adding and subtracting in my head. I'll think of it as a percent because that's easier to subtract. It's easier to think 100 minus 16 than 1 minus 0.16, even though it's really the same thing. But obviously, if we do, especially when it comes to multiplication, make sure that we are doing the math at the decimal level. All right, so that's where we get that those answers. All right, moving on. I'm going to need to talk a little bit about adding versus multiplying probabilities. So just a reminder, all probabilities are between 0 and 1. All right, that's kind of our baseline. All probabilities are between 0 and 1. If I take two probabilities then, and I add them together, that sum will be an overall increase. It'll actually will be bigger than both of them put together. It will be an increase because there are no negative numbers. So if I'm adding them, there are no negative numbers because it's all numbers between 0 and 1. So that means that it will get bigger. Or fine print, or stay the same if one or both of them are 0. So if one of those probabilities is 0, then obviously it won't get bigger. It'll just stay the same. So, okay, that's interesting. That means then that if I'm adding two probabilities together, this is going to lead to an outcome that is more likely to occur. Because remember, if my probability gets bigger, it is a greater likelihood of happening. It's easier to happen. It's getting closer to that 1 that's more likely to occur. Side note, I didn't write it, but make sure that when we add two probabilities, it doesn't get bigger than 1. If you're adding two probabilities together and it gets bigger than 1, you've made a mistake or misinterpreted the problem. With today's problems, we're not going to see that issue, but in some future ones that you will. So you always got to be careful about the situation. And there's reasons for that and different causes, and so we'll talk about that as we get there. All right, so then, again, remember, probabilities are between 0 and 1. So if I multiply two probabilities, that product will be an overall decrease. This is a little bit more jarring for some of us. Again, numbers, these are between 0 and 1. So imagine I take a half and I half it, I'm going to be at a smaller number. So it will be smaller. These numbers aren't negative, so they're not going to flip to be less than 0. But the big thing is they're not bigger than 1. If they were bigger than 1, then they might get bigger, right? They could stay the same if one or both of them are 1, because then when you multiply by 1, it doesn't change. So that's a little just trivial note. So this means that if I'm multiplying two probabilities and the probability is decreasing, that means it's leading to a probability that is less likely to occur, harder, rarer, less likely to occur. Take a look at these, the light purple here, just so you can see the math play out. If the probability of A, don't worry about what A is, just probability of A is 1/4, probability of B is 1/2. If it's appropriate for me just to add them together, then the probability of A plus probability B is 3/4. All right. Suppose that, and notice that 3/4 is bigger than both of those. So that is making it more likely, easier to happen. So again, if I have probability of A is 1/4 and probability of B is 1/2, and I was to multiply them, notice it's going to produce 1/8. 1/4 times 1/2 is 1/8. That is a smaller number than both of those. That is leading to a probability that is less likely to occur, harder, rarer to happen. All right? That is how I remember these upcoming rules, specifically about our addition and multiplication. Let's talk about the multiplication rule first. So with multiplication rule, it's when A and B are independent. Later, we'll talk about, not this video, but we'll talk about when A and B are not independent. That's a whole other issue. We'll call that the general multiplication rule. So this little caveat is attached to this. This is nice, easy, happy things, but has to be this independence thing has to be stuck on here. So if A and B are independent, then we can just multiply them together, and this gives us our and. This probability of A and B happening at the same time. So just to be clear about the term and versus or. So and is when I order a hamburger at a restaurant, at a hamburger place, I often will order mustard and ketchup on my hamburger. I hate mayo, and I want some sauce on it. I don't want it dry. So I will often order mustard and ketchup. So if that burger comes back, in order for me to be satisfied in my order, there better be both mustard and ketchup. If it's just mustard, just ketchup, mayo, dry, anything else on there, then that's not what I ordered. It has to be both for this and. So look at the picture here. This is this Venn diagram. So anything inside of this circle that I just circled is A. So if it lands here, that would be A happening. Over here, this is B happening. Well, I want to know when A and B are happening. So notice it's in that intersection, this purple section that I just highlighted. That's a probability of A and B. And mathematically, what happens, we get that when we can multiply these together. Again, let's go back. If things are just, I'm throwing dartboards and just making random hamburgers in the back, putting random condiments on it. If I'm just grabbing random condiments, whether it's just one or two or whatever, notice it's going to be less likely that I'm satisfied that I get both my mustard and ketchup and not anything else that I want on it. So that's why we're going to be multiplying it, because it's going to be making it harder, rarer to happen. And the math will also check it out. This is just a bit of an analogy to help it keep straight. A little bit of notation alert. I will just use the word and more often, but this is a symbol. This is like an upside down capital U. It's actually our intersection symbol. And this capital U is a bit thick and fat. So it's the intersection symbol. So that's our ands. You might see that symbol get used in some places. We need to talk about the term disjoint events because we're using it in the next thing. So disjoint is when two events cannot occur at the same time. So in probability speak, that's A and B is 0. So compare these two Venn diagrams, and you should notice that A and B don't overlap at all. They have nothing in common, right? So if they cannot occur at the same time, then there is there's what we call disjoint, or another vocab term that means the same thing, mutually exclusive. So in a standard probability model, these events are disjoint events. So in a previous video, I talked about these probability models like this. I can't get, if I'm rolling a six-sided die, I can't get a 1 and a 2 at the same time. Pardon me. I can't get a 1 and a 2 at the same time. So these, getting a 1 and a 2, they're disjoint events. In fact, all 6 of these are disjoint events from each other. I could say like, oh, I want to get a 1, 2, or 3. I'd be happy with any of those 3. That's fine, because then notice how I'm just going to be adding those together. That's what I'm going to show you just next, that or is the situation when we're adding. But getting 1, 2, or 3 is disjoint and separate from getting a 4 or 5, which is disjoint and separate or mutually exclusive from getting a 6. So in standard probability models, these are disjoint situations. So let's talk about this addition rule. So this is an addition rule when A and B are disjoint. Later, we'll talk about a situation when they're not disjoint. This is the nice, happy baby, introductory one. So if A and B are disjoint, then the probability that I get A or B, so here's our or here. Or means it's more likely, easier for it to happen. It's going to be raising that probability up. And so then that's our plus here. So we're going to be adding. So if I land here, I'm happy. If I land here, I'm happy. Later, when we talk about landing in both places, if it was an or, I had to be happy. So let me talk about that for a second. I like mustard and ketchup on my burger. Suppose it's being a little bit ornery on a particular day, and I said, put mustard or ketchup on there. If it comes back with just mustard, I should be okay. If it comes back with just ketchup, I would be okay. If it comes back dry, mayo, something else, no. The kicker is, if it comes back with them overlapping, both mustard and ketchup, and I said mustard or ketchup, I am also happy. That is fine. The logical definition of or is as long as I have a success, whether it's A by itself, B by itself, or both, as long as I have at least one success, then that satisfies or. There's a thing in math and computer programming and stuff, it's called the exclusive or. That would be me saying, oh, I want mustard or ketchup, but not both. I want A or B, but not both. Today, that's not a problem because A and B are disjoint. They can't happen at the same time. But in some other cases, that will be a thing. So just want to make sure we're familiar with or. They can happen at the same time. And then that's when we have to worry about that overlap when it's not disjoint. All right. So here for a little bit of notation, or is a symbol that's like just a capital U, a little bit of a fatter capital U, and that's It's a U because it's a union. Notice that the union and the intersection symbols are just flips of each other. It is this intersection symbol is a capital U just turned over, kind of makes it look like an in, a lowercase n. All right, so here's an example for this one. So again, 16% of the class are marketing majors. I have this caveat here that it's a really, really big class. So we're going to be treating these as two trials as independent, meaning when I select a marketing major, it's not going to, or if I don't select a marketing major, it's not going to significantly increase or decrease the probability of getting another marketing major. So it's just being remaining at 16%. I wish I kind of added that clarity, but it's trying to be probably simple for this question. All right, so we just said that if it's a probability of A and B happening, then we can just add those two things together. So let's just add those two things together. So here, I misspoke. Oof, let me rewind. If it's a probability of A and B happening together, I will be multiplying them together. So let's multiply them together. Sometimes you're talking and you hear yourself and you realize, oof, that's wrong. So sometimes I like just to write out what I'm doing. I'm finding the probability of getting 2 marketing majors out of 2 people. So that would be getting a marketing major and a marketing major. So if the probability of M is just this 16%, and what we just said that if it's this and they're independent, then I can just rewrite this as the probability of M times the probability of M. It's okay if A and B are the same thing. In this case, M and M are the same thing. We're just multiplying. So we end up with 0.16 times 0.16, and we get 0.0265. Over here in light blue, I did get my, I'm showing you how you can use exponents. This can be a thing that we'll see in a second that will matter. So if they are the same, you could, shorthand it to probability of M squared or 0.16 squared. I am putting these little extra brackets here because if this was function notation, we like to stick the squares in like this land, and I don't want to kind of be weird about putting squares here. So I'm just saying parentheses, kind of outside around it. All right. I don't have an example of it being of any ors in this situation, but they'll come up in a minute. All right, so let's talk about the probability of no success. Again, for independent events. So if A is the event that I'm wanting, again, let's talk about the term success. So if A is the event that I'm wanting, that's what I'm going to deem a success. Success doesn't necessarily mean a good thing. Suppose I'm a cancer researcher and I'm testing different samples that come through to try to determine for a certain type of cancer to see if there's cancer present. If I find that somebody has cancer, that's what I'm looking for. I'm looking for cancer, so I found a success, but that doesn't necessarily mean that's a good thing. When you test positive for COVID or for some virus or something, that's the test is identifying a success because it found what it's looking for. That's why we redeem it as a positive result, but that doesn't necessarily mean it is a good thing. So success is I found what I'm looking for. Failure is fine. I did not find what I'm looking for. So don't remove any good or bad connotation from that. All right, so then I'm going to say let P of A, the probability of A, be the probability of my success. All right, so if A is what I'm wanting, the probability of A would be my probability of success. Since it's an independent event, that probability is going to remain constant. In the future, and even as you saw on the website I showed a second ago, they used a lowercase p to represent the probability of success. And we'll even use a lowercase q to represent the probability of failure, where q is 1 minus p. Notice that lines up with our complement idea that if P of A is the probability of success, 1 minus the P of A will be the probability of failure. That's our complement. So this is the same thing, just kind of treating it as a variable, a little bit less to write, a little bit less complicated. Personally, if I was doing this, I probably would just be using the P's and Q's. But this section kind of keeps it with the probability notation. And then lastly, we're going to define N, just like how in our previous talks, N is my sample size. This is the same idea here for probability. It's the number of times I'm doing something, or it's my number of trials. So again, my lowercase n is my number of trials. Oh, and this P, just in case I didn't say it, is a lowercase p, whereas this is a capital P. All right, so I haven't revealed how we're doing it. In a second, I'll kind of reveal a formula. But like I said, this is like this says here, this is a learning example. So I'm going to find the probability of not rolling a 5 on a 6-sided die if I do 2 rolls, 3 rolls, or heck, let's go big, 14 rolls. So we're going to let A be just the event of rolling a d6, and I want a 5. And then, so that means the probability of A is 1/6, or just where P is my probability of success, let's just call that 1/6. What about my probability of failure? So the probability of not getting a 5, of getting no 5s, that would be the probability of a complement, which is 1 minus the probability of A. Since probability of A is 1/6, that's just 5/6. I know that's a lot of writing there for just to be able to go, oh, it's 1 minus 1/6, which is 5/6, but I want to be clear about this because we're about to have a lot of kind of 1 minuses happening. Or just in terms of P's and Q's, it's 1 minus P, which is then again our 5/6. So just to be clear, my probability of success is 1/6. Probability of failure is 5/6. Notice if I add them, I get 1. Those are all my options. I either get my success or I don't. There's no other option. It's either I get it or I don't. So let's talk about finding just 2. So I'm just going to roll my dice twice. What's the probability I don't get a 5 on either of those? So I could do, so basically, specifically, I'm not getting a 5, and then again, not getting a 5. So since it's an and then I'm not getting a 5, I'm going to be doing multiplying. Notice if I'm adding on this, tacking on this second event, thinking, okay, so I'm going to not get a 5, and then I'm going to not get a 5 again. Is this an add? Is this an add or a times? Well, if I tack on the not getting a 5, that is a harder, rarer, less likely event happening. That's why it's multiplication. It's an and, not or. It's an and. They both have to happen for this to be satisfied. So this is a lot of writing, and a lot of it is a bit redundant, just depending upon the notation or what you want. But the idea is if I'm not getting a 5, that's a probability of A complement. I've gone ahead and shown that they're both probability of A complement. So that's me squaring this situation. And honestly, I already know that A complement is 5/6. So I can go ahead and jump down here that that's going to be 5/6 squared. But I wanted to be clear that what I'm doing is what's being squared is 1 minus the probability of A, or 1 minus the 1/6. So of course, if I know it's this complement, I could just do this. But oftentimes, as kind of like I'm building a knowledge of our formula, I want us to see here that it's 1 minus my probability of success raised to my number of attempts. So notice there's about a 69-70% chance that if I roll the die twice, I don't get a 5. All right, so let's increase it to 3. So it's pretty much the same thing, but we now have an extra times A complement. So notice it should be pretty obvious that it's the same thing we just did, but instead of it being squared, it's now being cubed. All right. So now if I roll the die 3 times, there's about a 58% chance that I don't get a 5. Well, what about 14? I don't want to do this, times this, and then times it 11 more times. We can just use our exponents here and see that it's going to be the probability of A complement to the 14th power. Oh, I meant to, let me go and clean that up. I meant to put brackets around that. There we go. Just because I don't like putting an exponent directly on a function notation type thing. All right. So we already discussed how the probability of A complement is 5/6. So 5/6 to the 14th is about an 8%. So there's about an 8% chance that if I roll it 14 times, that I don't get a 5 in any of those 14 rolls. So let's generalize this. So this means that the probability of no successes in N trials would be equal to my probability of my A complement, or my Q, just raised to the nth power. Or in terms of the 1 minuses, or in terms of it, instead of it being the not A's, 1 minus the probability of A, or just my 1 minus P raised to the nth. So kind of 2 ways of thinking about this. Either it's the probability of the complement raised to the nth, because it happens n number of times and we're multiplying each time, or it's 1 minus the P of A, which you figure that out, get this, and then raise it to the nth. All right, No example for that, but I need that understanding for the probability of at least one. This is a popular kind of probability situation because it takes something that seems bonkers. How would you figure that out? And then there's a little back door that it's 1 minus the probability of no successes. So what we just talked about of the probability of no successes, it's that process, but we're going to do 1 minus it. So 1 minus the probability of no successes. So in symbol form, if you have the complement, you just do 1 minus the probability of the complement to the nth, or 1 minus q to the nth. Or if you don't want to do the complement part directly, it's 1 minus the probability raised to the nth. So it is kind of tricky with those 1 minuses in there. That's why I like to kind of think of it from the complement point of view. So let's go back up to our example we did here when n was 3. I'm going to draw a picture to help us understand this. So let me just go first to the picture. So the idea here is in my first roll that I have here in purple, I could get a 5 or not get a 5. There's a 1/6 chance that I get a 5, 5/6 chance that I don't. Okay. In my second roll, here are these possible branches. Notice after the second roll, there are 4 kind of paths I could take. I could get a 5 and then get a 5 again. There would be, if I multiply these together, there would be a 1 out of 36 chance, 1/36. I could get a 5 and then not get a 5. That probability, you would actually multiply these again because this is an and. I'm going to get this and then get this. So 1/6 times 5/6 is 5/36. Right? Or I could not get a 5 and then get a 5. Notice I'm going to get the same number if I multiply that. 5/6 times 1/6 is again 5/36. And the probabilities should be the same, but there are different paths. Getting a 5 and then not getting a 5 is the same probability as not getting a 5 and then getting a 5. But there are different paths. There are different kind of possible paths that could take to get there. And then, or here, look here, I could not get a 5 and then not get a 5 again. That's the most likely outcome. That's 5/6 times 5/6 or 25/36 as we saw a second ago when I just did my 2 rolls. But I'm going to do a whole other third roll again. I'm not going to go to each of those in detail, but you can see how each of these paths go, and we have a total of 8 kind of paths. Let me count the number of 5s that could happen. In this top paths, I ended up with 3 5s, 2 5s in this path, 2 5s, just one 5 right there. This one I have 2 5s, not 5, and then 5 5. So that's how I got 2 5s. These next two I only have 1 5. So not 5 not, or not 5. But then this last one is the most interesting one. This is the one that we just talked about of I want to find the probability of not getting a 5 at all. So notice it's 5/6 to the third when I multiply that out. That's the only one that does not satisfy my at least one. Look at my at least one. All of these work except for this one. So if I wanted to find the at least one, I could find this probability and this one 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 and this one, and then add them all up. And I can add them all up because they're all disjoint probabilities. One thing, we'll see the math for one in a second, but all these will add to 1 because this is basically, I can summarize this into a probability model, or all of these are disjoint, and this is the entire sample space, so they all will add to 1 if you did that multiplication all the way across, or basically all 36 out of 36 possibilities. So since all of this adds to 1, what I want to do is I want to find just this top part. But everything adds to 1, so if I do 1 minus this bottom part, I'll be left with this desirable part. And so that's what we're doing here. 1 minus the part I don't want. So I want to find the probability I get at least 1 win. I mean, at least 1 5. So what's the probability that I don't get a 5 at all? Well, the likelihood I don't get a 5 at all is 125 out of 216. So 1 minus that ends up being 91 out of 216, or about 42%. Obviously from here you can just use a calculator. So notice if I added up all 7 of these probabilities, I will get 0.421, or really I would get 91 out of 216. I don't want to do that, but I could just multiply these 3 things together and do 1 minus it, and I will get the rest. All right, let's take a look at this last example. At your school, Maybe not last. I think I have two examples. I have this one, and then another at least one. I just school 16% of the class of marketing majors. You randomly assign two partners. What's the probability that at least one will be a marketing major? So again, I'm gonna go to my picture first. So I could have a marketing major or not a marketing major. I could have another marketing major or not a marketing major for my second one, or not. So notice this top path, marketing major. I'm happy. I have two marketing partners. I could have a marketing major, not a marketing major. Still happy. I have one. Not marketing. Oh, marketing. Yay. I have one marketing partner. Sorry for the red dots. I clearly misspelled, or my app doesn't like how I spelled partner. So look at those probabilities. If I did 16% times 16%, I get this 0.0256. 16 times 0.84, or sorry, 0.16 times 0.84, I would get this 1344. 0.84 times 0.16, I get 1344. If I add these three numbers, I'm going to get my answer here. I know you haven't seen the work for it, but I do get that answer. But I don't want to do this work normally. As I just showed you, it's easier just to say 1 minus the probability of no successes. So 1 minus the probability of no marketing majors and 2 people. So I'm going to do the probability that I don't get a marketing major is 84%. So 1 minus the probability of that 0.84 to the second power. So notice this 0.7056, that's this path, my not-nots. Not. So the likelihood of getting 0 marketing partners is about a 71% chance of happening. Again, everything adds to 1. You can see the 4 numbers here. So if I added those up, I will get 1. Not like sort of kind of almost. It will be exactly 1.0000, exactly 1. So all of these add to 1. This is the one I don't want. So if I just subtract it from 1, I'm left with the sum of what I do want, which is this 0.2944. So I'm going to do this last one without drawing a picture. So for a sales promotion, the manufacturer places winning symbols under the caps of 30% of all of its soda bottles. If you buy a 6-pack of soda, what's the probability that you win something? So let's break this down. This 30%, that's my probability of success. That's P is 0.3, or my probability of win is 0.3, depending upon if you want to do probability notation or just treat it as a variable. Then I'm going to buy a 6-pack of soda. That means my sample size is 6. And then the probability that I win something, that's the key, that's the tip-off that I'm doing at least one win. If out of those 6 I ever win just once, I'm happy. 2, cool. 3, cool. 4, 5, or 6, all 6. I mean, obviously, the more times I win, the more happy I'm going to be. But I bought the 6-pack. By golly, I hope I win something. That will be deemed that's what I'm looking for. That I win something. It doesn't say the word at least one, but that's what you need to know using your English abilities to see that that's what that's saying. So look at here. The probability of at least one win is going to be 1 minus the probability of not winning anything. Well, what's the probability that I don't win anything? The win complement, or Q, is 0.7. So I'm just going to go ahead and jump. I'm going to skip over the second line because I think that math is a little bit weird looking. So I'm just going to jump to, it's the probability I don't win anything in six tries. So 1 minus 0.7 to the 6th. Again, I didn't write it in, but like in 6, sodas. So then I'm raising it to the 6th power here because I'm doing 6 total attempts. So there's about a 12% chance that I don't win anything. So, but what's the probability I win something? 1 minus that 12%, getting about that 88%. Again, it is a bit weird, 1 minus something. Those 1 minuses don't cancel out or do anything weird because notice I have to simplify this first and then raise it to the 6th. So 1 minus the probability of winning is 0.3. 1 minus that is 0.7. So that's why we end up with 0.7 to the 6th, and we get that. All right, so at least one is kind of an interesting, weird backdoor hack. Later in this course, we'll talk about how we can maybe do at least 2 or some other things using some other principles, but at least one, I'm always going to do 1 minus, for situations like this, 1 minus the probability of no successes. All right, I hope these basic probabilities, me going through these basic probabilities help in seeing these examples play out. Hope it helps, and I'll see y'all in the next one. Bye.